everyone, thank you so much for clicking onto the video. Here are today's learning objectives. So the first is to know the structure of an atom in terms of electrons, protons and neutrons, and to know the relative mass and relative charge of protons, neutrons and electrons. We then need to know what is meant by the terms atomic proton number and mass number, and be able to determine the number of each type of subatomic particle in an atom, molecule or ion from the atomic number and mass number. We then need to understand the term isotopes and be able to define the terms relative isotopic mass and relative atomic mass based on the carbon-12 scale. And then finally, we're going to understand the terms relative molecular mass and relative formula mass, including calculating these values from relative atomic masses. Now we're going to look a bit more into subatomic particles. So atoms are made up of three fundamental subatomic particles. And so we have protons, neutrons, and also electrons. And the protons and neutrons we've seen make up the nucleus, so make up the central part of the atom. And they are held together by a force called the strong nuclear force. And this is much stronger than the electrostatic forces of attraction that hold electrons and protons together in the atom. And so it overcomes the repulsion between the protons in the nucleus. And so that's how this strong nuclear force can hold all the protons together, because normally they would repel each other because they have the same charge. And another thing to know about the strong nuclear force is that it acts only over very short distances, so only within the nucleus. And then what we need to know about electrons is that they surround this nucleus, and they're found in a series of levels, which we call orbitals or shells, and these get further and further away from the nucleus. And so looking at this example of a helium atom, here we have a proton. So it's a positively charged subatomic particle which is found in the nucleus. And then this green one here is a neutron because it's also found in the nucleus, but it doesn't have a charge. And the yellow one is our electron. Because it's in a shell or an orbital around this nucleus. And so now we also need to look at all the relative charges and masses. So we need to know their relative charges and also their relative masses. And so here we have the subatomic particle. And so first looking at a proton, its relative charge is +1 and its relative mass is 1. And then we have a neutron, and its relative charge is 0 and relative mass is also 1. And then we have an electron. Which has a relative charge of -1 and then a relative mass which is much smaller than a proton and a neutron. It actually comes out to be 1 over about 1,840, so a lot smaller than the proton and the neutron. So you need to make sure that you know all of these relative charges and masses. Now we're going to look at relative formula mass. So the definition for relative formula mass is the weighted mean mass of the formula unit of a compound compared with 1/12 of the mass of an atom of carbon-12. So again, that's what we've defined as 1.0 exactly. And so it compares the mass of a formula unit to the mass of an atom of carbon-12. That's basically what the definition means. And if the substance is made of simple molecules, then this mass may also be called the relative molecular mass, which we've just seen. However, when we look at giant structures, we normally use the phrase relative formula mass instead of relative molecular mass. And we can calculate the relative formula mass by adding together the relative atomic masses of the elements in the empirical formula. So exactly the same as how we would work out the relative molecular masses. So for example, if we were going to work out the relative formula mass of sodium chloride, we would have that the MR of sodium chloride is equal to the AR of sodium added with the AR of chlorine. And so that equals 23.0 plus 35.5. And so that equals 58.5. And then for the MR of magnesium hydroxide, we have MR of magnesium hydroxide is again equal to the sum of all of the relative atomic masses. So we have the relative atomic mass of magnesium, which is 24.3. And then we have two oxygens. So we have 2 times 16.0. 16 is the relative atomic mass of oxygen. And then we have 2 hydrogens. So that would be 2 times 1.0. And so this gives us 58.3. Now we're going to have a look at mass number, atomic number, and isotopes. So these are 3 definitions that you really need to know. And the first is the atomic number. And we sometimes write this as Z. And this is just equal to the number of protons in the nucleus. And so the number of electrons in the atom is equal to the proton number. The proton number is also the atomic number. And so atoms are electrically neutral because we have the same number of positive charges and negative charges. And the number of electrons in the outer shell of an atom determines the chemical properties of an element and also what sort of element it is. And the atomic number defines the chemical identity of an element. And one really, really important thing to know is that all atoms of the same element have the same atomic number. So also because the number of electrons in the atom is equal to the proton number, when we look at the proton number, that means that we can see also that the number of electrons is the same. And then the second definition that we need to know is the mass number. And we sometimes call this A. And this is equal to the total number of nucleons. So what we do is we add up the total number of protons and the total number of neutrons, which are both in the nucleus, together. And it's the nucleons that are responsible for almost all of the mass of an atom because electrons weigh virtually nothing. So we saw that the relative masses of protons and neutrons were 1, and electrons were 1 over 1,840, which is significantly smaller. And then the last definition we'll need to know is the definition of an isotope, and that's an atom of an element which has the same number of protons but a different number of neutrons. So because it has the same number of protons, it also has the same number of electrons. And different isotopes of the same element react chemically in exactly the same way. And this is because they have the same electron configuration, because they have the same number of electrons. And atoms of different isotopes of the same element vary in mass number because we have that mass number is equal to the total number of nucleons, so protons plus neutrons. And because they have a different number of neutrons, all isotopes' mass numbers will be different. So for example, if we looked at a general element, so if we called this general element X, and what we would have would be, we would have A at the top and then Z at the bottom. So X is the element, and then we have A as the mass number, and then Z here as the atomic or the proton number. So this is how they're set out in periodic tables. So for example, if we actually looked at one of the elements in the periodic table, so for example, we looked at oxygen, and oxygen has a mass number of 16 and then an atomic number of 8. So now we can work out how many protons, neutrons, and electrons we have in this oxygen atom. So we know that the atomic number is equal to the number of protons. So for protons, this is equal to Z, which is equal to 8. And then for electrons, this is also equal to Z because the number of electrons is equal to the number of protons. And so this is also equal to 8. And then for the number of neutrons, we need to use the fact that the mass number is the total number of nucleons. So adding protons and neutrons together. And so that means the number of neutrons must be the mass number, which is A, and then minus Z. So it must be 16 minus 8, which is equal to 8. So we must have 8 of each of these subatomic particles in an atom of oxygen. And we'll also need to look at some ions. So for example, taking this oxygen, if we had an O2 minus ion, so oxygen likes to gain 2 electrons to form an O2 minus ion. And so for example, if we had O2 minus, and we still had this mass number 16 and the atomic number as 8, because these don't change when we add electrons. And so what we have is that protons stay the same. So we still have protons equal to the atomic number, which is equal to 8. But now the electrons, because they were the same as the number of protons, but now we have a -2 charge. So we have 2 more negative charges. That means we have 2 more electrons. So now it must be 8 plus 2. So now we have 10 electrons. And then the number of neutrons will also stay the same because we haven't altered the mass number in any way because electrons don't affect the mass number. And so we still have the mass number minus the atomic number, which still gives us 8 neutrons. Now I'm going to talk about relative atomic mass. So the actual mass of an atom is way too small to determine, and so that's why we use this relative atomic mass. And we compare their masses to a standard. And the standard we use is carbon-12. And we say that 1/12 of the relative atomic mass of carbon-12 is given the value of exactly 1.0. And so an expression for the relative atomic mass of an element is equal to the average mass of one atom of that element divided by 1/12 of the mass of a carbon-12 atom, which we've given the value of 1. So in words, the relative atomic mass, or the AR, is the weighted average mass of an atom of an element, taking into account its naturally occurring isotopes, relative to 1/12 of the relative atomic mass of an atom of carbon-12. And one really important thing to know is that all relative atomic masses used in calculations should be to 1 decimal place. So for example, we have that the relative atomic mass of oxygen is 16.0. And this relative atomic mass is actually just the mass number that we see in the periodic table. So for example, for carbon, it'd be 12.0, and for nitrogen, it'd be 14.0. So now we're going to talk about relative isotopic mass. So we've seen that isotopes are atoms of the same element, and so that means that they have the same number of protons and electrons. But they have different masses, and this is due to them having different numbers of neutrons. And we need to know the difference between relative isotopic mass and relative atomic mass. So we've seen that the relative atomic mass, the definition is the weighted mass of an atom of an element, which is relative to 1/12 the mass of an atom of carbon-12. And this mass, this 1/12 of the mass of an atom of carbon-12, we've defined to be 1.0 exactly. And so it takes into account every single isotope of an element, whereas the relative isotopic mass doesn't. So the relative isotopic mass is the mass of an atom of an isotope compared with 1/12 of the mass of an atom of carbon-12. And so the relative isotopic mass is just taking into account one isotope compared to the relative atomic mass, which takes into account every single isotope and averages the mass out. And so the other way we can define relative isotopic mass is the mass of an atom of an isotope of an element divided by 1/12 of the mass of a carbon-12 atom. So now we're going to have a look at relative molecular mass. And we can find the relative molecular mass by adding up all of the relative atomic masses of the atoms in the compound. And the relative molecular mass, or the MR, of a molecule is the mass of that molecule compared to 1/12 the relative atomic mass of an atom of carbon-12, which is what we've stated to be 1. And again, like the relative atomic mass, all MR values should also be given to 1 decimal place. And so another way we can express this relative molecular mass is having the average mass of a molecule divided by 1/12 of the mass of a carbon-12 atom. So the example we're going to look at is calculating the relative molecular mass of aluminium sulfate, which has the formula Al2SO43. So what we do is just add up all of the relative atomic masses. So we can find these relative atomic masses using the periodic table. So we have 2 times aluminium, which is equal to 2 times 27.0. That's the relative atomic mass of aluminium found in the periodic table. And this gives us 54.0. And then we have 3 times the sulfur, which is 3 times 32.1. And so this gives us 96.3. And then we have 12 times oxygen, which is equal to 12 times 16.0, which gives us 192.0. And so to find the MR, what we do is just add up all of these numbers. So we have the MR of aluminium sulfate is 54.0 plus 96.3 plus 192.0, which is equal to 324.3.